So guys, chemistry. What type of chemistry does a chemical engineer study? So that's very interesting because I literally saw about, I'm not joking, about 40 to maybe 50 syllabus, and the chemistry they study is completely crazy. There are some very specific, such as polymer chemistry and maybe even petrochemical chemistry, and some were just like basic insight, and even some syllabuses will only cover general chemistry and that's it. So yeah, once you get to meet a chemical engineer, it will be nice to see if he is a very specific, just the basic one, or maybe even not even that. So let's start. So these are the three chemistries that went up, let's say the most popular ones, and the least popular ones are, I would say, these right here. And the thing is that maybe this is my case, kinetic chemistry. I did not have a class for that. I had reactor engineering, and well, strictly speaking, this is chemistry. This is not reactor engineering. Reactor engineering is once you know kinetics, how to model reactors. And physical chemistry, that was also my case. I did not have a class for that, even though I know many of my colleagues do have a class for that. This will be either thermo number 2, or maybe they will also call it physical chemistry. This is essentially all the equilibrium stuff related for separation and heat transfer and mass or separation processes. So I took it, but I took it in mass transfer class. And organic chemistry, I did take one course, but I think there are maybe in one place I saw there were 3 courses of organic chemistry and even 2 labs. I don't know why they are so interested into that, but there were plenty. Analytical chemistry, it's either one subject with its lab, or maybe just one subject, or maybe a subject with lab, so it's theory and practice. My case was this one. I had one for theory and one for lab. So the only good stuff I know is about this analytical chemistry lab. General chemistry, I think, is the most, I'm pretty sure 90% of the syllabuses included general chemistry. And it makes sense because we are chemical engineers. I would say the problem or the thing here is that we are not strictly speaking chemical engineers. We are more like a process engineer. But the problem is that if you say you're a process engineer, they would think about processes or blocks. So you could be, I don't know, in a manufacture line. You could be working even in human resources processes. So process is so ambiguous. So that's why I think chemical engineering makes more sense. Now, electrochemistry, I didn't see that much. Nuclear chemistry was almost just an elective. Product materials chemistry, this is an interesting one. I did saw it, but not that much. I did take it. It was about how stuff is done, where, why, consumers, producers, so maybe, I don't know, general commodities, fine chemistry, pharmaceuticals, like general knowledge on the chemical industry, by how much is like tankers, tons, barrels, oil, distillations, and so on. But I will say this is maybe only 30% of the syllabuses I looked at were having these type of classes. Or maybe there were seminar for chemical production and so on. Polymer chemistry, I did not see it that much, but of course there's probably, I don't know, like I would say this is more about an elective that you want to specialize yourself in a polymer or polymerization chemistry. Well, there it is. Now let's talk about on what do we actually see on those courses, and recall that I did a very roughly average on what I understood the general chemistry courses had. So for instance, they talk about what's an element, a compound, molecules, mixtures and solutions, the mass numbers, electrons, neutrons, protons, about the periodic table as well, many of its relationships, recall the sizes and electronegativity trends, up, down, etc. We talked a lot of intra and intermolecular forces or bondings, which is very important, especially for mass separation, because you want to know if the molecules will interact between each other, and if mixture of molecules interact or do not interact. Those interactions mean energy, and energy means typically heat energy. So this is very important. Also the type of reactions, and as the name implies, once you get to know the reactions, you will be able to model reactors. So the type are essentially acid-base, precipitation, redox, which is reduction and oxidation, single and double displacements, and so on. Eventually, you see a little bit on reaction balances, which is stoichiometry, the famous Avogadro's number, changing 1 mole to maybe kilograms, and so on. The basics on equilibrium, what's an equilibrium, why do we need equilibriums, and so on. And the ideal gas law, which is how to model gases, why do gases depend that much on pressure, temperature, volume. Now eventually, well, I think analytical chemistry and organic chemistry are almost the same important in these syllabuses. So let me start with analytical chemistry. So essentially, we start speaking about equilibrium. Equilibrium is a very important part because we start analyzing acid-base reactions and buffers. And why do we need this? Because with this, we're going to do titrations, which is, let's say you have this period, you have the beaker, and you know this, and you know that A plus B turns to C, and let's say that C is purple. So you know the amount of A used, you don't know B, so once you know and relate stoichiometrically, and you see the color change, you can say that A and B reacted completely and turned to C, and since you know A, now you can get B. Gravimetric is pretty similar. Let's say you have A, which reacts with B, and you know that something goes as gas and something remains as a solid, so you just weight the solid and you know the relationship is 2, 1, 2, 1, so you have 1, you can relate with gravimetric techniques the amount of substances. Eventually also cation identification, remember cation is cations, solid, sodium, potassium, lead, silver, and so on. Then eventually what I think is the most important part, and we do not cover it that much, but I think it's just in general, is equipment-based analytical techniques, which is the things you will probably do when you have, say, this little test tube. Let's say you are the engineer in the brewery and you want to test this for ethanol content. You will not do it by yourself. You probably give it to a chemical technician or a chemist. He will use either of these depending on the standard of the industry and his knowledge, and he will tell you, yeah, sure, it's 4.5% by volume of alcohol. And you, as an engineer, will say, awesome, I'm inside the rule, so I can keep my, let's say, 1 ton, well, actually we're talking about liters, so let's say 10 hectoliters of beer. And I can ship them, and I'm a good process engineer. Now, organic chemistry is very, as I said, you can either study too much or study generally, depends on your aspirations. But the important thing is that carbon is the king in organic chemistry. We have plenty of families, alkanes, alkenes, aldehydes, ketones, carboxylic acid, ethers, esters, and so on. So I think this is good because this is present in plenty of petrochemistry. So when you have petroleum, you have a lot of organic chemistry there. And it's very important because petroleum, you know, guys, what petroleum means. It means money, it means jobs, it means a lot of international global markets, and means dependent of energy. So yeah, I will say organic chemistry is a very important class, at least to know the basics. And you will see plenty of reactions. The most common ones are hydrogenation, dehydrogenation, halogenation. This is adding chlorine maybe, bromine. This is take out hydrogens. This is add up hydrogens. Oxidation is, as the name implies, increase on oxygen. And you will see also mechanism of reactions. SNO1, which is like addition, and E1 and E2, which is elimination. So this substitution and this elimination, you will see maybe there's a molecule comes here, interacts with this guy and takes it off, and this guy gives something back and so on. You will see a lot of that. And once again, you need it because I will say mainly of extractions. Extraction, let's say liquid, you are using an oil in order to get kerosene. Well, you need to know a little bit on kerosene. What's kerosene? Where does it come from? Or maybe gasoline, you are a gasoline engineer. You know, this is between C7 and C8. Octane makes you a little bit, or octane maybe makes sense to you. Or maybe you are in a natural gas plant. Or maybe you are into petrochemistry, or you're a petroleum engineer. You are searching and you find, of course, you need to know a little bit on organic chemistry. Now we go to physical chemistry. As the name implies, is more about physical environment, but we are still talking about chemistry. So we're going to see a little bit on thermochemistry, which is thermodynamics. A lot of heat and temperature. We start understanding that heat is not the same as temperature. We start analyzing the specific heat of substances, especially that of water and gas, vapors or stream. Maybe you start to analyze the graph, the bell-shaped graph of enthalpy versus composition or temperature or whatever. Heat of reactions, you understand now that when you react something goes exothermic or endothermic. Heat of solution is another interesting one, is when you mix maybe A and B, and they still are A and B, but they are mixed, and there is a decrease or increase of heat, which means decrease or decrease of temperature. I will say we start analyzing phases and equilibrium. We start talking about triple point, what's a boiling point, condensation point, melting, freezing, sublimation. A lot of here this equilibrium between vapor and liquid, which is called volatility. Vapor pressure is related to that. We start to see some rules or laws, Raoult's law, Henry's law for mixture of gases, and a lot of interesting things such as Clausius-Clapeyron equation, many things related in order to model this. And why do we want to model this? Because of distillation, maybe flash operations, maybe even when you're using a pump. Many times you get a gas into a pump works only with liquid, so it will make a lot of damage to that pump. So that's why you want to understand physical chemistry. Now, kinetic chemistry, as the name implies, kinetic means movement or energy in movement. So kinetic is rate, how fast the reaction is taking place. So this one right here, the faster they crash, the faster you react, the better they crash in the best orientation possible, the better they create a product. So yeah, once again, speed of reaction, technically speaking, it's a rate of reaction, and yeah, it's a derivative because it's concentration with respect of time. A lot of stoichiometric relationship between the rates, Arrhenius law, which states the importance of temperature in the rate of reaction. We're going also to study the rate order, if it depends on first order, second order, or even zero order. Elementary rate law, which is basic for all the rate laws. We're going to start analyzing more mechanisms of reaction. How do A and B react to form C? Eventually, we also take into consideration catalysts, enzymes, and inhibitors, which are related to more speed or less speed. That has nothing to do with equilibrium, so that's very important, guys. And why do we need this? Well, as the name implies, we want to make reactions fast. How do we make reaction fast? Using catalysts or understanding the reaction, temperatures, pressures, heats. We're going to see that more in the reactor engineering course, which states how a reactor should be designed. Then electrochemistry, well, we will understand about the electron, how electrons make electric current, the Faraday constant, how to do a voltaic cell, or essentially a battery. You know, guys, a battery is essentially a beautiful chemical assemble that makes energy or electron flow. We're going to talk about electromagnetism and electric flux, and the EMF, which is the electromotive force, or that force that drives electrons to move and make work. Galvanization is a good application. So for instance, this right here, they have a very, very thin layer of let's say, a precious metal. And why do we want this? We don't want corrosion. So let's say we have this piece, let's say a golden ring, and you will probably see that normally in jewelry we do use 100% gold. But if we are using engineering application, let's say we are having this pipe, let's say this is the pipe, 100% iron. But iron rusts very bad, so we want to add maybe chrome and other materials, nickel, whatever you can think of. So this is 1% layer, and this will be let's say exposed to the oxygen, and they will react slower. So this is a good protection, and that's what galvanization is used for. Also, electrochemistry is very known for all metallurgy because we use a lot of electricity to produce copper, steel, and all those materials, precious metals, and so on. Now, nuclear chemistry, I'm not going to study that much because essentially what I will say the most important part is the energy-mass relationship. Yeah, the famous Einstein equation that states that matter can convert, or at least it has its equivalent in energy. And yeah, sometimes it's not 100% achievable, but we can get a little bit of mass into energy. And that is essentially fission and fusion. You need to know the differences, guys. One is at very high temperatures, which is still not possible, and this one right here, fusion, it's still possible in Earth, and this is not smoke, this is vapor. Anyways, and a little bit of quantum mechanics and Schrödinger equation and all that stuff that I don't think you will need in chemical engineering, but you might study it. Finally, I told you guys that I took a course on product or material or chemistry industry. We're going to see essentially what's a commodity is like oil. Oil is sold by a ton, and it goes up and down depending on the market industry. And fine chemistry, this is more about, let's say, pharmaceuticals. So 1 gram of aspirin may be about, I don't even know that, but let's say 10 cents, American cents. But you sell it up to $1. How come? Because you already have the fine application. The fine application is, I have a headache, I have money, I want to take out my headache. I'm willing to pay up to $1 to take out my headache. I don't care it's 10 cents, I want my headache out. And for the other side, for oil is, okay, if you sell me these for $80 the barrel, but this guy sell it to me to 79.9 US dollars per barrel, well, this is exactly the same, so I'm going to buy to this guy because he's 1 or 10 cents cheaper. So that's the thing about commodity and fine chemistry. And then, well, we start speaking about chloralkali industry, about how air, nitrogen, and oxygen is produced, at least to a very high purity, 99%. Whether you want pure oxygen? Well, in order to have very cool fuel output. Sulfuric acid, which is a very industrial or very common industrial acid, about metallurgy, how to make gold, iron, copper, steel, so on. Water treatment, yes, we take care about that. Also, the building materials such as cement and all those sand for construction, etc. Pharma also, and eventually I would say that many places I read in the syllabuses, especially those in the Middle East, even Egypt, and many in USA, they have an extra, let's say, course on oil and gas for exploration, production, distribution, maybe upstream data or downstream. They do take a little bit more attention into oil and gas. So finally, I think it's polymer chemistry. As I said to you guys, this is for, I will say, more about an elective or a specialization course. You might have it, I don't know. Well, what you're going to see is how polymers are built by addition, condensation, type of plastics, what can we do, thermoplastic and non-thermoplastics, synthetic materials, not from oil, or backwards, synthetic material from oil that we used to get from the nature, vulcanization, and so on. So guys, I think this is in general what we cover in chemistry in a typical chemical engineering bachelor. It's not that much, guys. Even though it seems a lot of subjects, well, many of subjects. So for instance, this one right here, you will see it in maybe reactor engineering or general chemistry. This one you will see it in, I don't know, equilibrium, thermodynamics, or maybe even in thermodynamics. What else? Electrochemistry, maybe you just use some, maybe 2 to 3 classes to just understand the basics. Nuclear chemistry, maybe you don't even take a course, maybe it was just one class inside your general chemistry course, or maybe if you are a nuclear engineer, well, of course you will have a lot of this. But what I want to show you is that chemistries are not in 1 year. You will not see all chemistries in 1 year. You will see it through all 1, 2, 3rd, and even 4th year. So no worries, plenty of courses for plenty of semesters.